this version of the algorithm working. I spent a little bit of time off stream getting it polished up, and I also wrote a shadow factor function which just computes a binary white or black shadow for the clouds, and we can kind of see that here. This should actually be in line with the shadow cast by the planet, but obviously, when you see this kind of shadowing in real life, it's not a perfectly straight line. There's scattering that happens along the shadowed clouds. I do think this is going to be the strategy I go with for the clouds because I really like the fact that it's completely like you can completely get whited out when you go inside of them. And also, I like the fact that when I'm compositing this, it's not transparent just because it's black. So if on the dark side of the planet I go into a cloud, it obscures the stars like it would in real life, which is kind of in line with the way I want it to behave. So that when we have our night sky, and I combine this with the atmosphere, our even on the dark side of the planet, our shadowed clouds will also obscure the night sky and whatnot. This isn't combined with any scattering yet. That'll come when we merge it with the atmosphere shader. It is going to be a big refactor when the time comes to do that. But this time, before doing that, I want to really get it polished up to my satisfaction. So the only thing left that I really feel needs to be done here is this shadowing needs a blend, basically. So that it's not just a immediate perfect line of shadow coming from the intersection with the planet, and rather it's a kind of a fade off. So I'm not sure how to go about doing that yet, but we're gonna talk to coworker and see if coworker has any ideas. So let's do that now. Okay, we have a cloud shadowing function. It correctly differentiates between the area of the clouds that should be shadowed by the planet. However, it is currently a completely binary output, whereas in real life, there would be some form of a fading, a fade in distance on the shadow. So that shadows directly on the border of the boundary cone of light blocks the planet would fade from their non-shadowed color to their shadowed color. Here is the current function. I need a way to make the uh, I need a way to make the transition from lit to unlit bit more gradual. Do you have any ideas? And let's see what coworker thinks about this. What bullshit? Don't tell me I'm unusual. Full of shit. Chat Jeopardy. Based on the proximity of the light ray to the planet's surface at the point of intersection, the gradient of the distance from the actual to the boundary of the shadow cone, modified version that includes a soft shadow. All right. Let's just see. Let's see how this works when we plug it in. What the fuck? What the fuck? Okay. Here we go. We're just gonna try this. If we can get this part right, then I think we're good to start integrating it with the rest of our atmosphere shader stuff. I like this because it's simpler. Um, right, that's definitely not it. Print screen. That just completely eliminated shadow contribution. Yeah. First. We still need to shadow the clouds properly. The example is the second which is exists. I assumed it would be like a dot product. Yeah, that's not right either. Number one, it's not even shadowing the correct area anymore. And in the quarter of the sphere that it is shadowing correctly. It is still the same abrupt transition. That there be something we do with dot product like that. Not sure. Stop. Bullshit. Shut up, coworker. Do your job. I'm gonna dock your pay. Dot product between the light direction ray from the planet's center to the sample point. Is to grazing the planet. Okay, this is what I was thinking. I thought that it should have something to do with the dot products. Give that a shot. Come on, work. Well, it sort of worked. Um, if we flip this, I think this is actually correct. Yeah, all right. Yeah, that's a lot better. Okay, that was almost right. And the alert colors order flipped. Needed to swap ambient right. Float ambient equals 0.02 maybe, and then we'll do. Oh yeah, this is great. We can control shadow softness here. Then one ambient and ambient. There we go. All right, that's starting to look right. Ambient's too high. There we go. Oh, oops, went inside the planet. And again, like the reason I like this model better is the consistency of flying in and out of the cloud layer. There's no inconsistency. So, like, it does exactly what you would expect it to do. Nothing is changing when you enter the cloud layer. No, like, no sample shifting or anything like that. And also, flying through the cloud is better. Like it fully obscures your it can fully obscure your vision, and also with the other one, the darker our clouds got on the dark side of the planet, the more transparent they got. But now even if they're fully black, they're still opaque, which is the way it should work. So when we integrate this into the atmosphere shader, we'll be able to incorporate the atmosphere scattering colors into it, and then we'll get the right coloration, and then I think we'll be in pretty good shape as far as our atmosphere goes. It's also a little bit simpler to control this. It doesn't have as many parameters, although there's a few that I still need to expose. I actually quite like this. It's pretty nice. And we don't have an atmosphere shader on here right now, so the white is very harsh on just a starry background. But I think once we get like our blue sky in place, it's going to start looking better. But you need up. All right, let me let you up. Here you go. Oh my God, pet chaos. All right, come on up. You can do it. Come on. Almost. Almost. Find it. Come on. Okay, you did it. She unplugged my computer. Okay. God, jeans. Chaos. All right, let me plug my computer back in. We'll get 0 frame rate if I'm not plugged into the wall. And then, okay, so I like our cloud fade now. It's doing what it's supposed to do. So let's take a look at. It's definitely better. We're going to need to clean up this code, polish it, maybe look for any kind of optimizations we can make real quick. We don't need all these comments, only the ones outlining like really important stuff. All right, sample cloud density, calculate sphere intersections, calculate height coefficient, calculate shadow factor. We'll just do this to, for consistency's sake. Okay. Phase function. I want to group this stuff that's used together, so we use our sphere intersects along with our calculate ray segments. So we'll put those together, and those are actually going to probably go at the top and move all of the density sampling stuff closer to the actual cloud trace. So our cloud trace is right here. We don't need these extra variables here. We can just, if we have to calculate them anyway, I think we can just do it this way. Okay. Is it scene? We don't need that. I do want to keep stuff like this. Is like when I define these float fours that have like arbitrary meanings for the XYZ and the A, it's good to like make a note that like XYZ is used for light accumulation, A is transmittance. Let's see. Not using total distance. So I've realized we can't have varying step sizes for different rays. It causes artifacts. And we also can't have a set number of steps. It has to be a while loop, which is less efficient, but it yields a much better result. So I think we can create a define. Um, Define step scale to let's see if I got my syntax right there. No. Shadow factor. Calculate shadow factor. And we may actually just remove the calculate from all these things. So the nice thing about this, I will say, is that okay, I can demonstrate the performance difference here, right? So you notice we get pretty good frame rate. We're flying around, and that's because we're able to short circuit a lot of our tracing. So rather than defining predefining segments and always marching the same segments, which we did some short circuiting in the other one as well. Don't get me wrong. Instead, now we define a length that we start tracing from the camera and a maximum length that we're allowed to trace, and then we trace until we pass that maximum length. But that maximum length has a lot of things that we can use to short circuit. The main one being the distance to the actual world position at that pixel in the scene, which would be the actual planet surface in our case. So, what does that mean? It means we perform really good, or not really good, but we perform well enough as long as we're just cruising around and we're above the planet surface, we're zoomed out, and we're able to cull a lot of our samples, right? However, if we go into the planet, all of a sudden we're not culling anymore, and the performance tanks. Ooh, it's junky. It barely works. So yeah, it this cloud rendering method will work as long as we are able to cull and short circuit a lot of the while loops that are happening. As soon as we're not able to do that anymore, we chug to a halt. And that's why I also have, once you get a depth within it, I just turn them off entirely. Um, but it's really hard to align that up with the surface when you consider that, like, you would need somebody walking on the surface to see the clouds, right? So I have it a little bit inside the planet, which means you do hit that laggy area. It's going to also be improved if I could figure out how to render this to a buffer, because then I could run a blur pass on it. But I haven't been able to figure out how to do that in Unreal yet. All right, so let's go ahead and clean this up. This is the complete cloud function. We'll be able to reuse a lot of this. Some of this stuff we may be able to define as well. Right, calculate sphere intersections, calculate trace segments. So, um, how many places am I using this? Occurrences, occurrences. If we're doing all these, shit. We're doing all these methods and they're all named calculate. I think it makes sense to just remove calculate, since that's just making it wordier. Um, occurrences. I'm honestly kind of finding myself on board with the philosophy of, like, you don't need a ton of comments, just comments on things that, like, you utilize that are kind of arcane or hard to understand, but, like, you should be able to look at the code and figure out what it's doing without having to read the comments. All right, we can shorthand this one. Um, Array sphere intersect x just to first intersect just to second intersect. Calculates the array segments needed to trace the current path through the shell formed by the min and max cloud radii. Uh, Returns float 4 with x equal to distance to array start y equal to distance to array 2 and at array 1 end z equals distance okay. Okay. Z equals distance to array 2 start. A perfect. Okay, great. I want to do this after our coefficients. It's gonna sample densities are the last thing we do before we enter into the actual tracing loops. So here we go. Thank you. It's a fade to fade to fade out the cloud density top. Well, don't need stuff like this. Fine. Cloud ambient. Doing it like this makes it easier to potentially make these exposed factors if we need them. So there we go. Why on earth would you do this? Sometimes the AI is pretty dumb. Like, why do I need a comment that this is the intersection with the planet sphere when the name of the variable is planet intersect? You know what I'm saying? Fun cloud shadow. Fun. Hey, buddy, why you keep jumping down and then I have to lift you back up? Oh, okay. Here you go. Oh, you did it. One jump. That's pretty good. That's pretty impressive. That's pretty impressive, little girl. You jumped up on the couch with one jump. All right. And we also want to look at things like this. So we don't need to do this dot product, right? If we're returning one anyway. So this short circuit, this is what I mean by optimizations, should come after we calculate our intersect. And we also don't need to planet center or distance to planet center. So these can move under as well. And now it should be a tiny, 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 tiny bit faster. It would, of course, be completely imperceptible to humans. But if we do that with every single method and we make every single method a tiny, tiny bit faster, we might net some kind of performance gains in the long term. Okay. So um, calculates the darkening from the shadow cone of the planet. Um, Ray March function to do our cloud light marching. Trace function to trace a single cloud ray. Traces any needed cloud rays for a given trace segments output. And there it is. I mean, that's pretty clean. What are we at? A little over 200 lines. 243 with spaces. Uh, I struct. External. Derived. Parameters. Cloud parameters. Cloud noise parameters. Cloud textures. Turns a flip 4. Alright, let's find everywhere we're calling normalize and make sure. Okay, that's correct. That's. Don't think we need these normalizes here. We're normalizing it up front. We can assume that these would be normalized. Okay, okay. Boop, boop. Work? Hey, we didn't break it. Amazing. All right. All right, so we're trying to clean up any unnecessary calculations that we don't want to do or that we can short circuit before. We're kind of ignoring a lot of clean code principles here to like grouping all your variables at the top and shit to just say, no, we don't want to be doing these calculations unless we have to. Let's take a look at this. Height coefficient radius. That's all fine. I think this is fine too. All right, trace cloud segment, distance travel. And so in our calculate ray segments or whatever, we are already incorporating our scene depth into our depth limit. So there's no need to worry about checking the depth limit or whatever. By the time we get to this, it will already be incorporated in the distance limit. So distance travel, distance limit, sample position, start position, camera vector, sample density. And then we check the density. We don't need to continue. I mean, That all makes sense. Um, okay, seems fine. Alright. Trace clouds, segments, step size, cloud radius, blue vector, blue offset. This all seems right. Cloud accumulation. Okay. Um, we can load seg1 seg length 1 equals seg length 2 C seg length 1 greater than 0. If seg length 2 greater than 0. So we don't need to run our cloud trace. I think it would just bail out immediately regardless, but we don't even need to run it at all if we have no segment length for that ray. Okay, there we go. This, go. Everything works. Nothing is breaking. And obviously, I'm not using my planet or anything like that in this scene. This is just a test scene I threw together to test the cloud shader we're working on here. Um, but now we're going to have to start looking into integrating our atmosphere shader back in. So save this. I don't need this comment. Samples the cloud volume noise formula at a given point. Density formula at a given point. Um, okay. You can make this a little bit more concise. Result, float 4 result equals float 4, -1, -1, -1, -1. Okay. Result.x. 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 Y. Result.y. 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 Result.z. Result.z. Result.a. Okay. Then we just return a result. A bit more efficient. Bit less variables created. Not really a huge deal, but the kind of stuff you clean up at the very end when you're trying to get ready to finish it. Okay. And all of those are based on basically this diagram of the different scenarios that we can have for our rays. Um, this shows kind of the idea of what the output should be in each of these varying cases. Excuse me. So if we are outside the atmosphere and we intersect the atmosphere, the outer atmosphere only, then your output would be O1, O2. negative 1 because we don't have a second ray. If we're inside the atmosphere, but we still only intersect the outer atmosphere, then our output would be the camera position O2, negative 1. If we're outside the atmosphere and we intersect both the outer and inner shells, then our output is O1, N1 into O2. If we're inside the atmosphere and we intersect both shells, then our output is cam position N1 into O2. And then if we're inside both shells, then our output would be N2 O2 negative 1. These are the different scenarios for where the camera can be and what our ray intersections are. So there's actually 5 different cases here that we have to think about when we do this, and that's what this function is doing. Is basically doing that calculation to return us the segments that correspond with those different cases. All right, so these two height coefficient. Okay, that didn't do it. Okay, and then this one. Okay, great. We got our height coefficient, our shadow factor. Sample cloud density. It could be that we need a remap here. But it's working. It's working. Light March. Um, I want to call this Cloud March. No, we don't want to do that. Um, Render clouds. Get them named properly. All right, I think this is pretty much done with code changes, at least for the cloud part. There'll be one more change when we integrate it with our existing atmosphere stuff to get the scattering coefficients for everything. But we got some nice fluffy clouds. You can fly through them. You can fly around them. You can look at them from the top or the bottom. We have a planetary shadow on the clouds. The dark clouds are fully obscuring the sky the way that I wished they would, which is really nice. Look at how cool that is. You can see it covering up the stars, which is super cool to me. Pretty happy with that. Okay, I think we're basically done with this part of it. So maybe next up we do a little tutorial in this piece of code, integrating it. Or do I wait till I've fully integrated it? I'd probably wait till I integrate it with the atmosphere because there's still a little bit of work to do. I have to integrate the scattering stuff. But yeah, I'm a fan of this. I think it looks really good. The other one also looked good, don't get me wrong. But the other one has some idiosyncrasies that I wasn't sure how to fix, and they're fixed in this one. So if I go to this level, you can see these clouds also look really good. Um, However, let's go into them. There's a few problems. Okay, one, we're not obscuring the view completely. Two, our view is inconsistent between exiting the inner shell here and entering the clouds and then exiting back out. Now, from outside, it looks freaking great, you know, like it looks really great. The other problem is that like there's always translucency. It's not We're not getting like fully opaque clouds. A lot of the stuff that's making these clouds look good is the integration with like the scattering, like you see here, where like the clouds in the distance are eating some of the atmosphere scattering. But we're going to integrate that into the other clouds, and I think they're going to end up looking better. And they fix the other problems that we were just pointing out, where like you can't go into them, they stay translucent, like the inconsistencies and such. Now they're just like, oh, there's a cloud there, and if you fly in that cloud, your vision's going to be obscured. You're not going to be able to see much until you leave the cloud. So yeah, pretty happy with this. Um, Probably take a break here and then come back a little bit later and integrate this with the atmosphere shader. But I'm pretty happy with this. I think it looks good. Obviously, we're exaggerating like the cloud height and things like that. We would actually probably be less than half of this height on an actual planet-sized object. Oh, no, no, no. The height was fine. Well, I don't know. It could still come down. The thickness. Exaggerating the thickness. That's a little bit closer to what you would actually see. We have a nice scene depth thing going on, so like there's no like it's just consistent. That's the key here is that like this version of it is just a lot more consistent in its behavior. Like look at it fading out as we exit it. It's not like a sudden thing or anything like that. We fade it out, we exit the cloud, and now we're down here underneath the clouds. Um, Looking forward to integrating this with the rest of the atmosphere shader. It's going to be cool. So, thanks to Sebastian Lague for making his excellent video. If anybody wants to take a look at that, it's right here. I pulled most of the actual. Um, let's see, what did we get from that? We got the way to accumulate the light and the density. We got the way to composite it with the scene. We had to write our own ray trace for the. We had to write our own trace for the actual area that's being traced because he was tracing his in a cube, and we can't do that. That's a lot easier than what we were doing. We needed to wrap around a planet. So we wrote the shell intersection method stuff, and we wrote the planetary shadow stuff because his don't obviously they don't have planetary shadows going on. Um, but this guy's got great shit. Like his whole channel is awesome. I've learned a lot from it. So yeah, I can recommend that highly. And I'm gonna go take a break and maybe play some video games or something for a bit, and then come back and integrate this with my atmosphere shader. All right, later.